This is our fifth class in this course on physics of materials, and in today's class we will begin our first attempt to create a model for the electronic properties of a material. Specifically we will focus on conductivity. As we discussed in the last class, there is a good reason why we are spending why we will spend so much time on the electronic properties, especially conductivity, simply because there is a lot of technological interest in this property, and there is also a lot of scientific interest because of the range of values that conductivity has. As I mentioned last class, between the best conductor and the worst conductor of electricity that you can find, there is a range of values of about 27 orders of magnitude, which is more than any other property, more than the range of values you will find for almost any other property that you are likely to measure for a material. So therefore there is a lot of scientific interest on the property that is conductivity. So for this reason we will spend some time trying to build a model for conductivity, or build several models actually for conductivity, and try to see what is the insight that we can gain into how various constituents of the material interact with each other and help us get a model and therefore a prediction on what the conductivity of a material should be. I must also emphasize that in our discussion so far we have specifically not included the special class of materials which are referred to as superconductors. That is something we will look at towards the end of this course. So when I talk of 27 orders of magnitude, it does not include superconductors. It is what we would call so called normal conductors. Okay, so standard conductors that we are more familiar with, a typical metal at room temperature and so on. The concept of superconductivity is very different. There are special aspects or special features that are prevalent when we say that a material is demonstrating superconductivity. It is very different from the normal mode of the standard mode of conduction that we see in the typical materials at room temperature. So therefore we would like to treat that as a separate topic. The kind of theory that explains it is quite different from what we would use for explaining conductivity at room temperature for most metallic systems. So I am excluding that. I just wish to alert you to that we have excluded it for now. Towards the end of the course we will have a class, more than one class perhaps, on just the aspect of superconductivity. So for now we will focus on conductivity in the sense that we are more commonly aware of, and specifically in the case of metals I mentioned that there is a positive coefficient of thermal coefficient of resistivity. So that is the conductivity that we are interested in, where when we raise the temperature of the metal, the resistance of the metal or the manner in which it obstructs the flow of electrons actually becomes more prevalent. So this is what we would like to explain. So we will, to do this, we will begin our first attempt to come up with a model by looking at something that we have possibly you have been familiar with from your high school days, which is that we describe metals and as being a situation or a state of the material where you have a free electron gas. Okay, so we hear this description, so we say that okay, so this is what we are often told, that metals behave as though there is a free electron gas inside the system, and so our attempt to describe metallic systems, our first attempt to describe metallic systems will take advantage of this description, or will at least work around this description. This is the general framework within which we will operate. So what do we mean by a free electron gas? So the way it is described to us, and which is the general format in which we will continue to use this description, is that in a metal we have all the atoms that go in towards making a metal, those atoms actually have some valency state, and to that extent they release an electron which stays within that material, okay, but is no longer belonging to a specific atom. So if there are 1000 atoms present there, and let us say each of them has a valency 1 plus 1 or can adopt a valency state of plus 1, then each of them releases 1 electron. So the 1000 atoms now together release 1000 electrons. These 1000 electrons are now free to run across the entire extent of that solid. So this general state we then refer to as a free electron gas state, where all those electrons, those 1000 electrons which are now freely running across the extent of that solid get together referred to as the free electron gas. So for example, we are just saying that we have an ionic core here, so we just have a schematic of a two dimensional ionic core, and let us say all of these have released electrons. So those electrons are actually running across this entire area. Okay, so this is what the ionic cores remain wherever they are, and the electrons are running across the extent of the solid. So this picture taken together is what we are referring to as the free electron gas picture. Okay, so in this system, originally when we think of a metallic system, we have those atoms sitting at regular lattice positions as we call them. So these ions continue to sit at those regular lattice positions, but they have released one electron which stays within this solid. So to use the term, kind of terminology they use for it, the electrons are still localized within the extent of this solid. In other words, they cannot run away from that solid. Okay, only if you extract the electron somehow and remove it away from the solid and take it to infinity, where it no longer can interact with this, or only then it has escaped the solid. So those electrons have not escaped the solid, they are sort of stuck within the boundary of the solid. So some solid boundary is there. So the electrons now stay within this boundary. Okay, so for our purposes they stay within this boundary, but at the same time they are not attached to any particular ion, any particular ionic core. So an electron that might have been released from this ionic core no longer actually specifically belongs to this ionic core, it runs all across the entire solid. So what happens is, now you have sort of positively charged ionic cores which in principle should repel each other and actually try to get away from each other. Okay, so that is the general tendency, because they are like charged, they will push each other away. The electron cloud as we describe it, or these free so called free electrons, they provide the negatively charged atmosphere within which these positively charged ions can now sit stably at some equilibrium distance with respect to each other. Okay, so this is how the picture of the solid is. You can I mean loosely we can think of it as some kind of a box within which we have contained a gas, so something like that you can think of. So that description is not very far from what we are attempting to use here. So these electrons are free to run around. Okay, so this is the general idea that we wish to use. So what we would like to do is to see if given that this is the picture, or to use the term, this is the model that we would like to that we believe that the solid actually has, we would like to put some equations, numbers, relationships to this model based on our best understanding of how these particles interact with each other, and see if from all those equations, relations and numbers that we throw into the system, we are able to get some prediction for how the conductivity of a solid, given this general picture of this solid, how will that conductivity be. Okay, so what is the kind of conductivity that we will get from it. So what we are actually doing is we are actually focusing on this word gas. Okay, so free electron gas. So gas is the word that we wish to focus on with respect to this particular description. Why I wish to highlight that is that we are actually quite familiar with, again from our high school days or even from our early college days, we are very familiar with this concept of an ideal gas. Okay, so we have this concept of an ideal gas, this we are very aware of we have a good sense of what it represents, we have a feel, we are very familiar with what equations go along with an ideal gas and so on. So but we are at least quite conscious of what it is and how we can what properties it may display, what can we extract from it, so to speak, what predictions we can make about it. So what we are going to do is actually take the rules or the behavior of an ideal gas, the general behavior of an ideal gas, all the rules that we associate with an ideal gas, all the behavioral trends that we associate with an ideal gas, and impose that on this free electron gas. Okay. So we are going to take the ideas, rules and concepts that we associate with an ideal gas, impose it on this picture of a solid, metallic solid which contains a free electron gas. Using this idea where this has been independently developed and by imposing it on this system here, we make our predictions. So from based on this we are able to make some predictions. Okay, so prediction. So we are that is our final goal, that is what we intend to do, we would like to make predictions. So based on this combination we would like to make predictions. So of course the minute we so to step back and see, what we are doing is we are taking rules associated with a gas and enforcing it on a solid. Okay, so we need to be very clear on what we are attempting to do. We are taking rules associated with a gas, and in fact not just any gas, rules associated with a so called ideal gas, and imposing it on something that we have never imagined as a gas. When a solid is given to you, when a solid piece of metal is given to you, you never intuitively think of it as a gas. Okay, so in fact in our mind it is clearly etched that a solid is not a gas, that is the very definition of a solid as a state of matter. But we are going to take the rules of an ideal gas, impose it on a free electron gas, on a solid, and then make some predictions, where we are actually not stretching ourselves too far is because we are not actually imposing it on all of that solid, we are actually imposing it on just the free electron gas, the free electrons, the so called free electrons which are now free to run across the entire extent of the solid. It is that set of electrons which are now freely running across the solid and therefore having some characteristics similar to that of a freely running molecules of a gas, which have some similarity. So based on, we are taking that similarity, taking advantage of that similarity to make this extrapolation. Okay. So now given this, we will add a little more, we will probe this idea that we can put this ideal gas behavior on a free electron gas a little more to see how justified we are in doing this. I have just descriptively tried to indicate that there is some similarity between this ideal gas and this so called free electron gas. So we will try and explore that idea a little bit more to see how justified we are in extending this idea of an ideal gas to a free electron gas, and we will also see if there is any reason why we need to be cautious of this extrapolation. Okay, so what is the aspect of this extrapolation that we should be little bit concerned about, so that at least upfront we realize that we can anticipate some limitations when we try and do this kind of an extrapolation. Alright. So we will first first look at the good news in terms of these two of this extrapolation, what is right about this extrapolation, so to speak. Okay, so we will now see in terms of a solid what is it that we are trying to how can we justify this extrapolation. Alright. So now let us take a solid which has a simple cubic crystal structure. Okay, so we will just draw that here. Right. So now at the corners of the simple cube there are atoms. So the general picture that we have is that we can put atoms which are roughly of this dimension. So we will just make those atoms touch. So that is what I am trying to do here. For clarity's sake, I will just stick to the atoms at the front face of this cube. There are atoms at all of those corners also, the other corners which are there. I have only put 4 here, there are 4 more behind. So just for clarity's sake, we will just stick to these 4 atoms for now and not worry about the other 4 atoms, fine. So the atoms have a radius r, and this crystal structure has a lattice parameter A. Now we are familiar with this idea of a packing fraction, okay. So this is something that we are familiar with, so we will just very briefly run through that calculation. So the volume of cube is simply A cube. When you have a simple cubic structure, you have 8 atoms associated, which are placed at the edges of this cube, okay. But given that each of them is now shared by all of the neighbors, if you actually run through how many neighbors each of them is shared with, you will end up finding that on average per cube there is 1 atom, okay. So that is what you will end up finding, that for on average you will have 1 atom per cube, because you have 1, 2, 3, 4 neighbors here and 4 neighbors on top. So 1/8 of this atom belongs to this cube, and similarly 8 atoms are there, so on average 1 atom. So the volume of an atom associated with this cube is simply, so volume of atom associated with the cube. So 4/3 pi r cube is the volume, it is one single sphere, we will assume spherical, atoms are all spherical, and then you will get 4/3 pi r cube. Given that the dimensions of this cube relate to the dimensions of this of the atoms, such that the atoms just about touch each other when they make this cube, we see that r is simply a/2. So therefore r equals a/2. So if you look at packing fraction, what we have here is, a packing fraction is simply the percentage or the fraction of the volume of this cube which is occupied by this atom, okay. So that is the packing fraction of this system. So if you look at it, we have packing fraction, so I will put it down here. So a/2 I have substituted for r, so you have a cubed by 8, and a cubed is the volume of the cube. So if we simplify, we actually have, so this is 2, so this is actually pi by 3 into 2, pi is 3.14. So we just want an idea of the value, we are not really interested in the exact precise value, but so approximately this is 1/2, because this is also about 3, this is also 3, so approximately 1/2, so this is approximately 50%, okay. Actual value comes out to about 52% or something, 51, 52, this is just an order of magnitude, we got 50%, fine. So if we take a simple cubic structure and we run through this calculation, we get about 50%, fine. This is one of the less packed structures, so to speak. So we will actually look at a more packed structure for a moment here. So if you look at a so called close packed structure, which is like the face centered cubic structure, FCC, fine. So in a face centered cubic structure, if you just look at the face of the cube, for based on symmetry considerations, it is enough if we look at just one face of the cube for our purposes. So a face centered cubic structure looks something like this. if you look through the calculations of how many, if you again see that every corner atom is actually shared by 8 other cubes. So 1/8 of every corner atom, and there are 8 corner atoms, there are 4 here, there are 4 in the other corners, so into 8, so 1 atom. And then the face centered atoms, each of them is shared by the adjacent neighbor, so half of this face centered atom belongs to this cube. So there are 1, 2, 3, 4, 5 and 6 face centered atoms, so 6 into half equals or half into 6, so to speak, to stick to this convention, half into 6 equals 3 atoms. So per cube there are 4 atoms now present, alright, and if you look at the relationship, this is root 2 times A, which if this is your okay, so this diagonal here is root 2 times A, so root 2 times A, because it is simply square root of A square plus A square, so 2A square root, so that is root 2A, that is equal to R plus 2R plus R, so equals 4R. Okay. So again, if you go through this packing fraction calculation, what we have is, so packing fraction here, your denominator is A cube, still the volume of this cube, that is A cube, okay. There are 4 atoms times 4 by 3 pi R cubed, and R is related like this, it is A by so this 4 will come down here, so 2 root 2, okay. So or we just put it down here, this is root 2A by 4 whole cube, okay. So if you simplify this, again we will just see here, I will just write it here so that we can cancel out what we need to cancel out. So this is 2 root 2 A cube by 4 into 4 into 4 by A cube. So we can just cancel these things out, A cube goes here, this 4, this 4, this 4 and this 4 will go. So we will have 2 here, and once again we will just approximate and cancel out 3 and pi. This is just an approximation just to give ourselves an order of magnitude. So we actually have, this is approximately 1 by root 2. Okay, so so this is what we will end up getting, 1 by 1.414 is what you will end up getting as the packing fraction. So this is 4 atoms, their volume 4 by 3 pi R cube, or you can even say root 2 by 2, so 1.414 by 2. So this is roughly about 75%. So this is root 2 by 2, if you just look at it as root 2 by 2, root 2 is 1.414, so you divide by 2, that is about 70 to 75%. So this is just an order of magnitude. So we get for simple cubic you get about 50% packing fraction, which means about 50% of the space is occupied by atoms, so to speak. In a much more packed system you have 75% of the atoms occupying the space. Okay, so now if you look at it, if you look at all the metallic systems that you, if you look at the other one, the BCC, which we will not go into the calculations, it comes out to about 62%, oh no actually 68%. 68% is the packing fraction that you have for BCC. These are all approximate numbers. Okay, so all I wish to point out is that you have numbers of this order, 50%, 68%, 75%, approximate numbers of the packing fraction. If you actually run through the correct calculations, you may get more precise numbers, but this is what you are looking at. So what you need to understand is that these are for example solid objects that you find. Okay, so solid objects like this. So this is a metallic solid object that we have. So this is just a rod, okay, a rod of a metal, and this is a part of a gear. Okay, a part of a gear. It's a failed part, so this is being actually some analysis is being done on this part. So this is a part of a gear, and this is a spring. Okay, a very strong, powerful spring, so strong that it is very difficult to even press with your hand. Okay, so this is a spring. So these are all solid metallic systems, metallic objects that you can locate and you can find easily find. So when you lift them, when you hold them in your hand, when you look at them, it is difficult to imagine that anything like 50% of it, 25 to 50% of it is actually open space. Okay, is vacant. So when you say a packing fraction is 50%, when you say packing fraction is 50%, it means 50% of the volume of that system is occupied by atoms, the other 50% is empty. Okay, so this is not something that intuitively occurs to us when you look at a solid object. When you look at this solid object, if in case this had been a simple cubic based structure, okay, there are very few metallic systems that fall in that category. I believe polonium is one of them, but if this were such a structure, 50% of this, half of this would be vacant empty space. That is not something that we intuitively imagine when you see it. Even if you say quarter of it is empty, again it is not something that is intuitively known. Okay, so but that is the fact. When you actually run through the calculations, you find that there is that much of vacant empty space present within this solid object. So when you go back to our picture that we say that there are ionic cores, and then the rest of the volume of that solid is actually being freely occupied by all those free electron gas, the electrons that have been released by those ionic cores, and actually once the atom actually releases the electron, its radius will actually slightly decrease. So we will actually have to use the ionic radius here. So in fact, in principle you can think of it as even more space now being available for the electrons. So even more than 50% may be available for those electrons to run across the entire volume of that solid. So therefore, from the perspective of a packing fraction, when you recognize how much of that solid is actually vacant, from that perspective it is not a very unreasonable thing to treat the free electron gas as behaving in a manner that mimics the ideal gas. Okay, so where we actually look at the fact that in ideal gas the atoms run across the volume of that container that they are contained in, and they have a lot of free volume to run across. When you make that comparison to that solid, even though in principle we know upfront that a solid is a different state of matter, even though we know that, when you realize that 50% of the solid is vacant or could be vacant depending on that crystal structure, 50% of it could be vacant, and those electrons which are very tiny, please remember an electron is extremely tiny relative to the molecule of a gas. When you take that into account and you assume that it's freely running across that half the volume of that solid, from that perspective alone, this link between an ideal gas behavior and a free electron gas behavior does not seem very far fetched. So therefore, at least to start off with, it is not an unreasonable thing to extend the ideal gas ideas to a free electron gas which happens to exist within a metallic system. So that is the first part of what we would like to highlight. At the same time, I think it is necessary to recognize the reasons why such an extrapolation should be taken with a degree of caution. And now look at the reason why we need to take this extrapolation from an ideal gas behavior to a free electron gas behavior inside a solid with some degree of caution. Okay. So to do that, what we need to consider is the what we need to get a feel for is the number density of particles. Okay. So we will just see what we mean by that. So let us take for example an ideal gas. What we are told of an ideal gas, or what we are aware of for an ideal gas, is that at STP, so 0 degrees C and 1 atmosphere pressure, standard temperature and pressure, 0 degrees C and 1 atmosphere pressure, an ideal gas will occupy 1 mole of an ideal gas occupies 22.4 liters. Okay, so that is the volume occupied by 1 mole of an ideal gas. So now we will run through some numbers. 1 mole implies 6.023 Avogadro number into 10 power 23 atoms of gas molecules or whatever. So, 1 mole is 6.023 into 10 power 23 atoms in this case. Let us assume an atomic gas. So, we will have this. So, some ideal gas we have. So, so many atoms are present in 1 liter. Okay. So, in 22.4 liters at STP. So, let us see the number density that we are looking at. So, we have 6.023 into 10 power 23 atoms in 1 liter, and 1 liter is I mean 1000 liters is 1 meter cube. So, we will run these numbers on a per meter cube basis. So, 1 into 10 power I am sorry 22.4 into 10 power minus 3 meter cube. Okay. So, 22.4 liters 1 mole is contained in 22.4 liters, 1 mole has so many atoms. So, so many atoms are now contained in 22.4 into 10 power minus 3 meter cube, fine. So, this is approximately if you look at it we are looking at approximately 3 into 10 power 25 atoms per meter cube. Okay, 3 into 10 power, so this is 2.24 into 10 power minus 2. Okay, so that would go up there, so that would make it 10 power 25, and 2 and 3, 2 and 6 would give you the 3 there. So this is approximate, just because we are only interested in the order of magnitude really. So 10 power 25 atoms per meter cube is what you are looking at, 3 times 10 power 25 atoms per meter cube. So this is for an ideal gas, right. So now we will look at the other possibility. Let us take a solid, in fact a metal for which we are trying to impose this kind of where we are trying to extrapolate this ideal gas behavior to the free electrons present within that system. Okay, so an example that we will take of a solid system would be silver. Okay, so we will just take silver. Its density is approximately 10.5 grams per centimeter cube. Normal and its atomic mass is approximately 107 atomic mass units, so 107 AMU, and normally valency commonly demonstrated by it is +1. Okay, so valence state is +1. So in other words, if you have a block of silver, it is reasonable to treat it as though every atom in that silver in that block has released one electron for the so called free electron gas. Okay. So now given this information, we will not worry, we will just use this density and atomic mass to give us an idea of the volume we are dealing with, and we will take use of the fact that again 1 mole of this substance would have released per atom, it would have released 1 electron to this free electron gas. So we will have an idea of the number of electrons, we will have an idea of the volume they are contained in, and therefore we will get a number density. So since this is a solid, all we are saying is that we will just go over this. So this is so many grams per centimeter cube. So we will convert this to grams per meter cube because we would like it in atoms per meter or particles per meter cube. There we got it as atoms per meter cube. We will, in this case we will get it as electrons per meter cube. So to do that we have 10.5 into, so this is centimeter cube, 10 power minus 2, each centimeter is 10 power minus 2 meters, so 10 power minus 6 meter cube. So this is, it will become 10 power 6 grams per meter cube. That would be in the denominator, so it will go to the numerator. So many grams per meter cube you will have of silver, and if you divide this by its atomic mass 107, that will give us the number of moles of silver per meter cube, number of moles of silver per meter cube, and if you multiply this by your Avogadro number, this now gives us 10 power 23, I am sorry. this now gives us the number of atoms of silver per meter cube. Okay, so this is the density of silver, this is the atomic mass, so therefore number of moles per meter cube, and then times the Avogadro number gives you the number of atoms of silver per meter cube, and assuming that every atom has released one electron, effectively the same number will be there, same number of electrons per meter cube will be available to us. Okay, so if we just run through these calculations, what we see here is again this is a similar kind of number, so this is we can treat this as 10 power minus 1, so this is 10 power 5, so this is approximately 6 into 10 power 5 plus into 10 power 23, so 10 power 28 electrons per meter cube. Okay, so if we just run through this calculation, we get 6 something into 10 power 28 electrons per meter cube. So if we do not worry about the 6 and 3, essentially we see that in an ideal gas we have about 10 power 25 entities, in this case atom, per meter cube, and in a solid we have 10 power 28 electrons per meter cube. In other words, there is a 3 orders of magnitude increase in the number of particles per meter cube. Fine. So in a solid the electrons are 1000 times more densely packed than the atoms in a gas. Okay, so that is a difference of 3 orders of magnitude, 1000 times more densely packed electrons relative to the atoms in a gas. So this is the reason why we need to be cautious when we extend an ideal gas behavior to these so called free electrons which are present, the free electron gas that we believe exists inside a solid. So there is a difference in 3 orders of magnitude or 1000 times more densely packed electrons are present within this solid relative to what is present here. The reason why this is something that we need to be cautious about is because in an ideal gas we make statements, and which we will do right even now, that the particles do not interact with each other. Okay, so they are isolated enough from each other, even though I mean they do interact with each other, but they do not unduly influence each other. We basically say that they collide with each other, but after the collisions, between the collisions, there is no further interaction between the particles. Okay, so they do not influence each other between those collisions. Now the more densely you pack those particles, the less reasonable that statement becomes. Okay, so the more closely the particles are packed, there is a greater chance that they will actually interact with each other even between the collisions. So therefore the kinds of things that we say for an ideal gas now slowly become less and less reasonable to say about a system where you have electrons which are much more closely packed, 1000 times more closely packed. So we have actually 2 pieces of information. One is that most of the there is a lot of vacant space present within a solid, and therefore on that basis it is reasonable and interesting to extend ideal gas behavior to study electrons in a solid. At the same time, even though there is that much space available, the electrons present within the solid are about 1000 times more densely packed than the atoms present in an ideal gas. Therefore that provides us with a reason to be cautious about such an extrapolation. Okay, so both these things are there, we need to keep both of them in mind. So it is not unreasonable, but at the same time we need to be cautious about this whole process. Fine. So with these 2 ideas in mind, we will just put down now the kinds of rules that we will expect our free electron gas to obey, and based on those rules we will then develop our theory for a free electron gas, and therefore predict the conductivity of the material, especially a metal, based on our extrapolation of ideal gas behavior to a free electron gas. So we will just put down the rules today. We will then have to take some tangential deviation to develop a few of the ideal gas concepts that are of interest to us, and then impose them on the free electron gas. So we will go into our ideal gas behavior a little bit in the next class, and then we will come back again in the class after that and impose that on the rules that we are now going to put down, and see how the equations develop. For metals, is based on some assumptions. Okay, so the first assumption that we put down is that undergo electrons undergo collisions with each other okay. So, electrons undergo collisions with each other which are instantaneous and these lead to scattering. Okay. So, the first thing that we say about electrons as they behave as part of a free electron gas is that they undergo collisions with each other, and as a result of these collisions the electrons scatter. Okay. So, they scatter meaning they go all around the place before they bounce off of the other electron. So, this is one thing. These rules that we are going to put down, you will see that many of these rules are very similar to what is being stated when you develop the ideal gas behavior, so to speak, the equations for the ideal gas behavior, and that is the reason why I highlighted that upfront. Between scattering, between collisions, interactions with other electrons and ionic cores is neglected. Okay. So, between collisions, interactions with other electrons and interactions with ionic cores is neglected in its details, in the details. And I think this needs to be explained a little bit. What we are saying is between once an electron has collided with another electron and has bounced off, till it makes the next collision with some other electron which is randomly moving through the solid, in between there is a certain amount of time that it is travelling between two collisions. In that time we are not specifically writing any detailed equations on how it is being influenced by other electrons around it, being influenced by the ions around it. Okay. So, however, we do put in an averaged term. Okay. So, we do put in some kind of an averaged resistive term to account for this general interaction, but we are not specifying anything in any great detail. Okay. So, so therefore, some aspect of this ideal gas kind of behavior we are still maintaining. Okay. So, the detail of the interaction is neglected, but some averaged interaction is being accepted or accounted for. Okay. So, that is what is important. There is something that we call the mean free time between collision. So, okay, so the mean free time between collisions is represented by tau. So, this is the average time between collisions. So, an electron, as I mentioned, bounces off of one electron of another electron, then travels for some time, then hits a third electron. Okay. So, this is going on for all the electrons within the system. At any given time the duration between two collisions will vary for all the electrons. So, some we may travel a longer distance before they hit the next electron, some may immediately hit the next electron, and so on. So, this happens. So, we cannot actually, since there are so many electrons within a solid, we cannot actually individually note down the numbers for every single electron or attempt to put numbers down for the same. So, what we do is there is something called the mean free time. On average, this is the time that an electron travels between two collisions. okay, it will have a collision, on average it will travel this time before it has the next collision. That average time is tau, and that is independent of the position and velocity of the electron, okay. So in other words, and this is reasonable because by definition this is mean free time, this is just the mean average, okay. So clearly if velocity is higher, the chances that it might hit another electron may be higher, but that is all accounted for the fact that based on the fact that we are using the mean free time, okay. So this is the third assumption. Electrons attain equilibrium with their surroundings using these collisions with other electrons, okay. So, so therefore the collisions are important, you cannot just completely neglect the collision, okay. So the collision is, so that is the reason why we are putting these rules down. We wish to highlight that they are the electrons are free to run across the extent of that solid, there is a lot of vacant space within the solid and the electrons are free to run through the solid, and as they do so they collide with other electrons, okay. So those collisions are instantaneous, in other words there is no time that we are associating, we are not saying that when the electrons hit each other for 1 second they are next to each other, we just say instantly they hit and they bounce off, so that is instantaneous, and this causes scattering, so the electrons run all around the place because of those collisions. Between the collisions, the interaction between those electrons is being neglected, the interaction, so there will be some repulsive interaction between the electrons that is being neglected, there will be some attractive force between the ions present in the solid and the electrons that is also being neglected, and that is not unreasonable because as we mentioned even between the ions there is a force of repulsion, but the electron cloud effectively which has the same amount of charge as those ionic cores, the total charge of all those ionic cores is the same as the total charge of that electronic cloud, so they sort of cancel each other out, which is true even for the electrons, okay. So even for a single electron that is running around, there is a large ionic core that is present within the system, large set of ionic cores, and there is also a large electronic cloud. The total negative charge and the total positive charge more or less cancel each other out except for this one electron's charge, so largely it is running in a more or less neutral system surrounding. So therefore the interaction is being neglected in its details, but an average resistive term is being included, which we will see when we actually put its value down. And there is a certain mean free time between collisions which is independent of position and velocity of the electrons because it is the mean free time as we described. And finally the reason we need to focus on the collisions is because that is the manner when the two electrons collide they exchange energy, okay. So there is an exchange of energy, so one is gaining energy, losing energy, the overall energy is conserved but there is an exchange of energy, and that is how the electrons attain equilibrium with their surroundings. So when you take a block of metal and place it in a room that has a certain temperature, let us say this a block of metal was cold, you take it out and keep it in a room which has a higher temperature, it is only because of these collisions with various electrons and so on that slowly the heat begins to permeate into the system. The electrons which are very close to the surface of the metal sense the temperature first, they gain energy which is reflected by their velocities, how they move and so on, and they go on and collide with other electrons. The ionic cores also participate in the process, so which we are not addressing at the moment, but for our purposes we will focus on the electrons at the moment, later we will see what the ions do, but we will focus right now at the electrons because the properties we are going to focus on depend on those electrons, the specific property that we are looking at the moment. So they attain equilibrium with their surroundings because of the collisions, and therefore it is important to keep track of the collisions, we cannot completely neglect those collisions, okay. So that is the basic idea, and so these are the broad rules that we will take, they have a lot of similarity with the rules that ideal gases have, and that we impose on an ideal gas or we expect an ideal gas to demonstrate, and the very same rules we will now impose on the solid and on the electrons in the solid and see what kind of behavior those electrons demonstrate, and based on this model we will now be able to predict specifically the electronic conductivity. We will also predict the thermal conductivity. These are two major properties that we predict, and we will see some interesting relationships between them. So it is with this background that we will halt here. In our next class, since we are going to use some ideal gas behavior, and specifically we will use specific quantities or relationships from an ideal gas behavior which will be relevant here, we will develop those specific quantities briefly. Then we will come back to these assumptions, impose those quantities on these assumptions, and on that basis we will develop the electronic conductivity. That will be 2 classes from now, and 3 classes from now we will look at thermal conductivity. So that is how it looks going forward from here. Okay, thank you.